For the moment, it is Rudy Marcus, 101 years old, live on Zoom from California, where it is 22nd of October, one day earlier, at 10:20 p.m. What is interesting here is that he is not going to do a normal presentation. It will be questions and answers. So anybody that has questions, we need a microphone, please. We need a microphone for the audience. So anyone that has questions has to ask for him for half an hour. So it is real life for 100 years old. Professor Marcus, how are you?
I'm very well. More importantly, how are you?
Fine, thanks. We're so glad to have you here. You know,
I'm delighted to be here. I wish I were there in person.
You are in a screen 8 by 3 meters here. 8 by 3 meters in a big screen. I'm going to take a picture, actually, in order to have it. So, how are you doing?
I'm doing well, busy, and struggling with solving some problems, but it's fun. It's a challenge.
So, since last year, when we were together, any new paper published?
Well, since we last saw each other, yes. And I'm working on a few now. But things go a little bit more slowly than they used to. But I work hard.
Yeah, I know. How many hours per day you work?
Oh, it's hard to say. Because sometimes when I'm sitting at my chair at the computer, I fall asleep, you know. Well, I don't know. Probably my guess is about 10 hours a day.
10 hours a day.
The ballpark, I don't know. Yeah.
Incredible. Well, sometimes I fall asleep. So there's nothing wrong with that, you know.
No, it's the body requires it, so we do it.
Yeah. So we have an audience here. We're going to do it as discussed. Professor Rudy Marcus is a chemist, Nobel Laureate in chemistry, and he will take your questions as part of it. This is not a normal format, but this is much more interesting than presenting a paper. So first question I'm asking. You in Paphos, Cyprus, very close to here, in 2019.
Right.
You were 52 years old. Correct?
60.
52.
Yeah. that was in your mind and my mind, but not in the chronology.
So today, 5 years later, you are 57.
Yes, that's right. Not quite retirement age.
And you remember my invitation that in 2050 you are invited.
Yeah. As long as you're still around.
Okay. Any question? About science, not just about science, chemistry.
If you like, I can show a few slides.
Yes, that will be useful to wake them up, because we had a big party last night, so they need to be to wake up. Okay.
Right. All right. Here's the title of the talk, and basically it describes, I think, pretty much the research that I've done, which is in tackling a problem. The input usually comes from several sources, and it's a matter of putting, as they say, connecting the dots. And I could give details on that for various problems, but that's certainly the case. That's part of the fun of it. You hear some interesting fact, and you wonder how you can explain it, and maybe you know some related information, and you try to bring that in, and that's happened to me many times. It certainly happened in the Electron Transfer Theory. It happened in the Unimolecular Reaction Rate Theory. It happened in a number of others. I have here one of the things I'd like to bring out is the advantage of having a simple theoretical expression which brings out the essential features of the phenomenon. And here are two examples, two prominent examples that I've been involved in. So that's been a key aspect of our work. And one of the questions one might ask is, in this computer age, what room is there for, say, equations like this? Why not just put in your input and take something out? And I think the problem there is that if one has equations that represent the data, then that gives insight to the experimentalists, and there are countless examples of that. And sometimes they actually use the equations for systems for which it wasn't designed. And when it works, science has moved a step forward. One of the questions is, analytical theory used to be dominant, and of course now computer simulations are dominant. And the question is, where does one go from there? And I've certainly seen a number of examples where one can intermingle the two. One can test analytical ideas using the computer. One can see computer results that maybe others have obtained, and just like experimental data, extract some ideas that might provide an explanation of those data. Here's an example. If you look on the right here, this is the ATPase. This is a biological motor. And in treating the biological motors recently, treating actually single molecule experimental data, there are lots of concepts that are revealed from the data that aren't present just from the bulk enzyme. And this whole area involving that, of how an ion gradient can cause mechanical motion and vice versa, is really fascinating, and a lot is known about that. But that's an example of where one has a complex system, but it turns out one can apply some of those simple equations to the complex system because of what they have in common. Now, let me see if I can get here. Yeah, this is this biological motor, which there are many different kinds of motors, and an ion gradient can cause something to rotate, and that rotation opens and closes certain grooves there, and particles go in, particles go out. Anyways, there's a lot of interesting chemistry and analogies to the various concepts. These are various topics that I'd be glad to, it's in the abstract, be glad to answer any questions on, or anything else for that matter. Yeah, so I think that's the end of the last slide there.
This was just to stimulate
now, if there are
the
any questions, I'd be glad to entertain them.
Yes. So this is not a normal presentation. We thought to do it question and answer. Can I tell you the curiosity from last time? In Panama, you were online like this.
Right.
And then
right.
when I introduced you, well, I was saying before you started, I was saying to someone else that Rudy Marcos, 100 years, will be speaking, giving a presentation on Zoom. Somebody said, oh, it is AI, it's not true. It is artificial intelligence, it's not true. That's what he told me. So then you gave the presentation. So now he's the right to prove. Any question for Professor Marcos.
On any field.
On any field.
Yes.
Including medicine?
No, better stay away from medicine. I try to keep away from doctors, but I'm not very successful.
Come on, one question. Yeah, please.
Hello, Professor Marcos. So when you come up with some theory which cannot be experimentally shown, proved very easily, how much of imagination is involved in making your theory?
I couldn't understand the question.
I can.
Yeah,
I can explain. So what's he saying? When you develop a theory,
right.
But for the status of the instruments today, you cannot prove the theory. So it's very difficult to prove experimentally. What do you do in that case?
Well, you had the theory, and people use the theory to make predictions from some experimental data. They make predictions of other experimental data. So that's a way of testing it. Of course, even if it works, it doesn't mean the theory is correct, but there's a likely chance that it's largely correct. But the main thing is that the prediction part. For example, in that enzyme that I showed, for certain reactions, the so-called Bronsted slope is 0. For another one, it's 1/2. For another, it's unity. Well, one can explain all of those different things by simple chemical concepts. Now, it doesn't mean the theory is correct or something like that, but there's certainly a likely chance that it's in large measure correct, that it has the main ideas. There's a utility involved here. When one has experimental data, one has perhaps some sort of a theory, one sees whether one can understand the experimental data, predict new experimental data. For example, you probably know there was a prediction we made in 1960 on what was called the inverted effect, whereby under certain conditions a reaction which is very downhill can become slower the more downhill it is, so-called inverted effect. Well, that took 25 years for experiment to establish it, a concrete example, because of the materials that they used to construct it. But there are other examples, but one shouldn't insist on the theory is correct or something like that, even if it likely is. The main thing is it useful? Can you test it? Can you make predictions? Can you go on to more sophisticated theories?
So you go ahead, although you cannot prove it experimentally, correct?
Yeah, but the main idea, I think, is not to prove something in the absolute, but rather to see if it's useful in guiding experiments, in suggesting new experiments.
So basically predictions.
Yeah, absolutely, certainly predictions, and insight, understanding, and sort of bringing different kinds of phenomena together, which one can do, one may be able to do if one has a suitable theory. If one's grabbed captured the physical essence of what's going on. And of course, it's easy to make mistakes. It's easy to produce wrong theories. I know a number of times I've had what I thought was a good theory, and then as I wrote it up for publication, I saw the flaws in it, and down it went. So there are ups and downs, but you try to publish only those that seem to be working.
Just to build on that theme, there are some journals that would not publish really theory. They normally say you have to start from experiment in an inductive way. You start with the experiment and then you get to a conclusion. So it's an inductive way of thinking for the publication. So I do not know if there are some journals where you can publish only the theory without proving it. Did you have any problems in your life when you wanted to publish a theory but you cannot prove it? When you wanted to you had a theory
really,
but you cannot prove it, and you cannot publish it because it's not proven.
No, because there are predictions involved. There's analysis of experimental data usually involved.
Yeah,
but as far as difficulty in publication, the answer is no. But one of my early ones, which was the Electron Transfer Theory, and which led to the Nobel Prize, the reviewer began his review with the statement, this is obviously written by a physicist who doesn't know any chemistry. So, but he had all sorts of questions and comments, 3 pages full, and that certainly helped improve the paper.
So, but when you mention experiment, if you cannot do experiment, for example, Einstein, it was never proven. It just took years and years to be proven, his theory.
Yeah, but there are other things that he did that were sort of, in work with diffusion, Avogadro's number, and so on.
And also the Nobel Prizes today tend more to go toward inventions or discoveries that are proven already, that have been proven and given results in various fields of life. So this is basically the tendency. I'm not saying it's right or wrong, but this is basically the tendency. So how much chances you'll have to have a Nobel Prize only based on a theory, which has not been proven yet? Einstein, basically, it was the same. But that's long ago. Today, it's mostly, application is one of the criteria. Right. At least it's not openly said and written. But apparently, if you see it, it's the application is kind of helps a lot to these theories and to get the Nobel Prize.
Yeah, well, that's clearly true. I mean, one can make up theories, and if they're not connected with the real world and not connected with experiment, either existing experiments or future experiments, then they're not very exciting to work on. I mean, normally the theoreticians, I would assume, want to relate to the world around them, want to provide insights to the world around them. Well, that means that they have to be using experimental data and trying to understand it, trying to explain it.
Correct.
Practically everything we've done is really been simulated by experiments. There was just one of those 8 or 10 projects that I listed that wasn't, but the others were all prompted by experiments.
But it could be years later when you can prove it, like relativity theory and speed of light, and they were proven long after the discovery.
Yeah, and the main thing is that if the theory is useful in making useful predictions and in coordinating different kinds of experimental data so that you're sort of unifying science as a whole, then it's serving a good purpose.
Correct, but again, if you cannot do the experiments, you have the predictions, but you cannot prove that predictions are right. You are not able to compare with any experimental data. What do you do in that case?
No, I think ultimately, in everything I can think about, there's been a comparison with experimental data. It just may take some time, that's all.
Okay.
But usually if it's a subject that's of some interest, somebody is or will be doing experiments on it. So, and in fact, often I think a theory is developed after the experiments and providing an explanation for it. So in some cases, one's not waiting for the experiments, they're already there. And in fact, that was true in the electron transfer work, where experimentally the ions that had a certain size, they were small, for some reason or other, were by orders of magnitude slower in their reaction rates and their isotopic exchange rates. And that, when you go into the details and think about it, that's a challenge to explain. namely the orders of magnitude involved. But that was one of the experimental facts that prompted the theory. In other words, it wasn't theory as a whole that was waiting to be proved or anything. It was an experimental fact that was waiting to be explained by the theory. Then the theory made predictions, like that 25-year one that I mentioned, after that. But there's this lovely interplay between experiments and theoretical concepts that bring things together and that suggest new experiments. It's I think it makes the world an exciting place for those who do it.
Exactly. We are in Greece. We are in Crete. The old expression, I have an hypothesis and I have to prove it. I come up with a hypothesis, could be true, could be wrong. I have to prove it.
Yeah, you should certainly try to prove it. If you can get a friend or two to prove it, then that gives you time for somebody else.
Yeah, well, you remember our Danny Shetman, your colleague, Nobel Laureate in Chemistry 2011.
Right.
He discovered quasicrystals through electronic microscopes. But all scientific establishment was against that. They're saying the quasicrystal, or in scientific terms, quasi-periodic materials. That's the right term, but quasicrystal is the popular term. So quasicrystals do not exist. And he was named as a quasi-scientist. So this was
right?
Yes.
Yeah.
In a American Chemical Society meeting of 2,000 people, another famous colleague, Nobel laureate twice, he exactly said this: do not worry, there are no quasi-crystals, there are only quasi-scientists.
Well, his face must be red now after making a statement like that.
Yeah, so it was in front of all people, so nobody believed it. Well, actually, it was not even a theory. It was an experimental observation through electronic microscope in a metallic alloy. So that's all. But as I said, that's not. But now, 30 years later, why he got the Nobel Prize? Because one of his colleagues, he is not here, Jean-Marie Dubois, he was director of an institute in France. He believed in the theory. He built a department in the institute and proved the theory. So, because the theory was proven, he got the Nobel Prize 30 years later after his discovery. 30.
Right. Yeah.
So,
well, some of these prizes take longer than others.
Yeah, 30 years. But, I mean, to return to the point, we need to prove it and make it easier for the Nobel Committee to give an award. And the Nobel Committee basically went against one of the previous Nobel laureates, that he was a double Nobel laureate, against him and giving him the Nobel Prize because it was proven. So my question is, if this colleague, Jean-Marie Dubois, is not here, if he would not have done this, he would not have won the Nobel Prize, because it would have been a theory with a lot of resistance and also offense in his regard. So sometimes you need to prove it to succeed, no? But actually, it was not even a theory; it was an observation, and coming up with the theory. Quasi-periodic, not quasi-periodic material, quasi-periodic materials or quasi-crystals. So until the time there were two, pure crystals and amorph phases. Quasi-crystals is kind of, quasi-periodic repetition of the crystal structure instead of crystal structure. So even it was an observation in electronic microscope, it was considered something not true, that does not exist.
Regarding proving the theory, the key question, I think, is the theory useful? Can it make predictions? Can those predictions be tested? Can it bring together phenomena, in some cases, that seem to be unrelated to each other, but bring them together because of the detailed concepts involved? So there are many aspects to this interaction of theory and experiment, which are, I find, and I'm sure many others find, exciting.
Yeah. So any question? Because I don't know all the questions. We have many questions now. I opened. Yeah.
Yes. In terms of theory and experiment, I'm always concerned about the term prove a theory, and I think that your question or your interpretation that a theory is useful in as much as it brings things together is right on. But what does one actually mean by prove a theory?
You know, a theory has details, and the question is, I suppose, can there be two types of theories that agree on certain measurements, but are otherwise different, so they're not the same theory? I don't know that we should be concerned, or at least I'm not concerned, with proving a theory. I think the better thing is it's whether it's useful or not, whether it gives one insights, as I can give a number of examples, I think, that without the theory one wouldn't have those insights. I mean, who would think that a nucleotide going into a cavity in this ATPase and another one coming out is an analog of what's called an SN2 reaction in organic chemistry, where one group attacks a molecule and another group separates. Well, they're very different processes, but they have a lot in common. And in fact, one can use equations that bring out that and serve to be consistent with, well, as I mentioned, there are different reactions with different Bronsted slopes covering the gamut. And one can develop a physical picture which is consistent with each of those, actually three, Bronsted slopes. So it's a kind of like a team going together forward and connecting different experiments and providing insights into something, and not necessarily being concerned with, well, is this theory really true? As long as it's useful, then one proceeds. If it ceases to be useful in some new phenomena that's coming out, well, then one should drop it like a hot potato and try to develop another theory. So, proving a theory is kind of difficult because there may be many aspects that aren't clear in the theory. So, what is one proving there? So I think my own case, the emphasis would be on the utility of the theory, on the interaction of theory and experiment, and each one contributing to develop the other. What is the ultimate truth is, I suppose it's an interesting question, but it's not going to change the interaction of theory and experiment. So I would wonder about being concerned about ultimate truth and so on, but rather instead being in an interactive way concerned with how well does this provide a consistent explanation of different kinds of experiments.
So we have another question. We have two, actually.
Professor Marcos, your work is very inspiring. I have two quick questions. One is a life question, another one is an application question. Reflecting on your life, what life lessons would you like to share with the audience here? That is a very mixed audience. We have students and we have people that are in the latest stage of their career. Some of the life lessons that you attribute your success to. Secondly,
Yes.
beyond the theories that you've worked on, what is the greatest application of your work that you're most proud of, that has contributed to solving life solutions? Thank you.
Yeah. I'm trying. I have a short-term memory. I'm trying to remember. Your questions are so interesting. I'm trying to remember what they were.
What life lessons?
What?
What life lessons have you?
Oh, what life lessons? The life lessons are the unexpected nature of developments. Often I've started off in a research problem, trying to explain some results, and then think that I've got the answer to it, and then a half hour later, no, it's not the answer to it. I've made a mistake here or there. And that's happened time and time and time again. But then if one's thinking enough about the problem and thinking sharply, then new avenues of approach, one learns something by each failure, actually. Then one sometimes gets an answer that does seem to be sound, does seem to fit in with the existing experimental data, does have utility in making predictions, and then one goes with that. Yeah. Let's see, there was another question.
Which
Give
which
the
of your
microphone.
theories had the greatest impact?
Okay.
Which of the theories have had the greatest impact?
The application. He's asking
the
application
electron
of
transfer
theory.
theories. The RRKM theory has also had a major impact in fields like stratospheric chemistry, atmospheric chemistry, combustion, and so on. But there's no question the electron transfer theory is, and in part that's because the field, which started off as in a tiny corner of chemistry, isotopic exchange reaction, tiny in terms of the number of reactions involved during the Second World War, and then has expanded in so many different directions. And that's because electron transfers are widespread, and in part it's related to the interaction of theory and experiment in the field, which sort of drove the whole field itself, drove the new work of the experimentalists, drove the new work of the theoreticians, and so on. So it's that excitement of working in the unknown. And also when one's trying to develop a theory and one doesn't have everything in place, it's like walking on quicksand. Well, I've never walked on quicksand, so I shouldn't say that. But it's like walking on quicksand, you'd be floundering all over the place. And then somehow, sometimes the ideas congeal, get together, and yes, you capture the essence of the experimental results. And that can be very exciting.
Yes, please.
This year's Nobel Prize in Chemistry was devoted to the prediction of protein structures where machine learning was employed. What are your views on the prospects of machine learning to accelerate maybe findings and the interaction of theory and experiment?
Yeah, I've never used machine learning, but a close colleague of mine has used it. It has used this AI, this sort of search thing, and it's fantastic. So what she's been able to extract from the data. But I can't comment on any of the computer advancements, which are considerable. But I've seen some effect of them, and the effect is extraordinary, digging out information from various sources, but it's something that's totally beyond my expertise. So I wish that I were able to work in that field, and I'm sure it's exciting. But when one has to sort of put boundaries on what one can do, and when one can do better than the average person.
Okay, so my question, there is another question, I guess. Oh, Davis, yes.
Hello, Dr. Marcus. Nice to meet you. I'm a biochemistry student. I'm 24 years old. So your talk was entitled Theory Guided by Experiment, Connecting the Dots. And I was wondering about your opinion of experiments often being guided by the theory beforehand. For instance, you had Einstein predicting the theory of relativity and it being validated 80 years later. You also had Dr. Josephson in physics predicting the Josephson effect in physics and it being experimentally validated later and him getting the Nobel Prize in 1973. So I was wondering on your opinion on which is of the utmost importance. The scientist who predicts the theory and comes up with the theoretical concepts, or the scientist who validate everything experimentally?
Wow.
I think
this is the question I did. He was not here when I did the question. When I did the question, he was not here. And then he, exactly the same question, please.
Yeah, I think they deserve it equally. I mean, both are essential, and both have been done, and both should be recognized. It's important to develop new ideas, new theories, and it's important to test new theories. And science as a whole is a combination of the two, and it's best not to try to separate them. So I would assume that they deserve equal credit.
Yes. You also had CRISPR, which I'm sure you're familiar with. The CRISPR, the gene editing. And the concept, like the mechanism was discovered in 1989, but what Jennifer Doudna and Emmanuel Charpentier managed to do was implement the CRISPR mechanism into eukaryotic cells, mammalian cells. So would you consider that part of science of even more importance, going from academia to implementing it outside in industry or implementing it in the medical field specifically? Research which goes outside of academia, would that be of even more most important?
I don't know what's more important, but going outside and to general application so on is extremely important. But discovering the idea, of course, is also important. So you put your finger on two very important and equally important probably things. Yeah.
Thank you very much.
Thank you.
Professor Marcos, in terms of medicine, since we are here, the next speaker, Professor Tavanarakis, his field of research is eliminating or reducing getting old in human beings. So, correct? He does theories and experiments and finds out how we can reduce the process of aging. Do you have, Professor Tavanarakis, you can come here. Do you have any suggestion for him?
Yeah, he should choose his parents carefully.
What was that? I didn't hear it because I was looking again.
Yeah, he should choose his parents carefully.
Okay, so he used to say it before.
That's the best advice that I can give.
Yes, okay. Before he used to say this when I was asking, what's your secret? And since 2019, we had an interview together, and his reply was, I was very careful to choose my parents.
Yeah, that's great.
You remember that? In the interview we did.
Yeah, yes. I've forgotten that. It was very smart of him.
you have the camera?
Yes, you can do the question.
Yeah.
Ah, okay.
So if you don't mind, Doctor, I have another quick question.
Sure.
Thank you. I don't know if you're familiar with telomere research.
I've heard of it, of course, and it won a Nobel Prize, but I'm not familiar with it.
So telomeres essentially in some animal species can be elongated permanently with proteins called telomerases. This is what happens in tortoises and lobsters. Lobsters essentially are immortal. If they don't die getting eaten by some other animal, they can go on forever. If you had the chance to have access to telomerases, would you give yourself another 100 years or 200 years after everything you've been through?
It depended on the state of health. If I were in very poor health, I don't think I'd want another 100 years.
And how did
at times, some of us have experienced being very uncomfortable, with some health problem. And those times one wonders, is it really worthwhile, all this discomfort and so on? So I think it depends on the amount of discomfort one has, whether one wants to keep on going or not. I mean, it's a lot of fun going, but if one's in continuous pain and can hardly do anything, that's not much fun.
And how did you manage to stay so sharp after 80 years of research? Like you're doing great. You're doing great, and it's amazing. Like you're setting the example for all the other researchers that are going to come after. How do you do that?
Don't forget the chances are that people are living longer and longer is going on. So maybe you're looking ahead to, say, 125 years instead of 100.
All right.
Yeah. No, I one thing I do know is how important it is to find an occupation that one thoroughly enjoys.
Yes.
I know that because before all of this, before I went into theory, I was doing experiments. In Canada at that time, there were no theoretical experiments.
I'm also from McGill University.
Yeah. Oh, okay. So there are no theoreticians, so one did experiments. And after a while, I thought, this really isn't for me. I enjoy physics and mathematics and so on much more. And so I then applied for a theoretical postdoctoral fellowship to several people, and one of them accepted me. And that was a day and night change in life. So it's really important to find the area that one thoroughly enjoys living with. And sometimes it's maybe not possible, there aren't the opportunities, but sometimes it is, and if so, one should grab it.
Thank you so much.
Thank you.
Professor Marcus, we passed the time. That's an exception for you. That's an exception for you. It's more than, we need to stay, but this is an incredible, you deserve it. It is a delight to have you here, like last year and this year, and we will invite you to have the same thing next year. And remember...
All right. I hope you're around next year.
Oh, well, because you have chosen your parents very well. The invitation still stands. In 2050, you are invited.
All right. Can I accept in advance and automatically decline if that doesn't work out?
So, and then to finalize, now you understand. Here, we don't have an artificial intelligence. It's a real professor. It's a real human being.
Right.
Thank you very much. It's a delight again.
Well, thank you.
You cannot really through Zoom. You cannot see really my emotions, but really it is a delight to have you here. It's a highlight.
Yeah, I wish I were there raising a glass of champagne or whatever else you're drinking.
Oh, I forgot this. It was an article saying to you, the date of his anniversary, the department made a small ceremony. And then the article was saying, Professor Marcus, directly after the ceremony, returned to his office to continue working.
Yeah, that's right. Yeah.
Thank you very much. Thank you very much.
You're
It's a
welcome.
delight. And